Hello everyone, my name is Yahui Song. I'm soon becoming a fourth-year PhD student. My research interests are mostly program verification and different kind of temporal logics. I'm very happy to share my current project with everybody. And this is a work actually under submission right now. It's also a joint work with my supervisor, Prof. Qingwei Nan. Also, during the presentation, please feel free to scan the QR code on the right-hand side corner, which contains a web page of some examples from our implementation. All right, we are trying to do some automated temporal verification, not only capture the execution sequences, but also introduce the real-time awareness into an analysis. That's why we call it timed temporal verification. And also our target language is a language called hiphop.js. It is a very new language recently proposed in PLDI 2019. It is essentially a combination of synchronous language, Temporal, and some asynchronous primitives from JavaScript. Temporal is a language used for modeling and circuit design. Then JavaScript, like many other mainstream languages like C#, it introduced these asynchronous primitives for us to write non-blocking programs but still maintain a sequential programming style. Then hiphop.js, this language was originally designed for web applications, reactive web applications. It shows that it makes the code, based on the combination, it makes the code more concise and also makes it easier to understand. Although those criteria are pretty subjective, but I personally find it's pretty convincing. That's why I'm really interested in this language, but also this language programming style, the mixed synchronous and asynchronous concurrency model. That's why we started to work on this direction. All right. In a typical temporal verification framework, rather the verification framework I'm interested in, is we are given two things. The first thing is a source code P, and the specification, we call it S. And in the most cases, the specification is to describe the desired behaviors of the program, of the implementation. And in most of the cases, it is abstracted as an automata, or sometimes it's the abstract algebraic language, which is expected to translate into automata. And what we are trying to do, the first thing is we need to infer the actual behaviors from the implementation, so that we call it B, so that we can capture the real bugs, the behaviors from the implementation, not instead of like there is a gap between the modeling and the real implementation. Then we need a prover for us to prove that the inclusion relationship between the real behavior B and the specification S. And checking the inclusion problem between B and S proves that the program P will never lead to unsafe states, will never have unsafe traces, which violates S. And in the most typical cases, this is based on the automata theory, because the specification S and the actual behavior are all abstracted into automata. Then from the prover, it has three possible outputs. The first one, the true, means that this is checked. So there is no unsafe traces generated from the real implementation. Or false means there exist traces are unsafe, violates the specification. Or unknown means this is undecidable upon the current computation power of the prover. Then the automated verification means that we only take the input, the source code P and the specification S, and the output we get is the feedback from the prover, leaving everything in the middle, including the inference process and also the proving process, all automated. Based on this framework, we highlight our contributions using these orange stars. The first thing is we propose the novel effects logic, which is called timed effects. So we use this logic to capture the behaviors from the program and also some non-trivial temporal properties. And the second contribution of our work is because this language is very newly proposed. So we build the first semantics model to capture the behavior from the program. Based on this axiomatic semantics, we abstract the actual behaviors from the real implementation. And last, we provide a term writing system to prove the inclusion between B and S. And also our backend solver is proven to be sound and complete. That's why the output does not have any unknown answers, either true or false. So in the rest of the talk, I will be talking about the details following the indexes showed here. The first is, let's look at the example of the logic first. So one typical safety property can be specified as that the certain events will be triggered no later than a certain amount of time. So in our representation, we use curly braces to represent a time instant. Then every event within the same time instance will be regarded happening at the same time. This is the concept from the synchronous programming style. Then here we bound this trace, which is a multiple repetition of this empty instant followed by a time instance containing events down. By bounding it using a time t, and t has t is a symbolic term which has a constraint on it. We essentially specifying that this event down will be happened before 1000 milliseconds. Next, if let's say we have a function called send, it takes an input d, it's an integer d. So we specify that this d is smaller than 5000 milliseconds, and we use this time t to bound the execution, the real time of this time instance. Then this t is smaller than d. So in that case, our time bound can be dependent on the program input and also can have its own time bound constraint as well. So we can find that this from the syntax of our logic, it is essentially extends the synchronous cleaning algebra with this operator sharp to introduce the real time abstraction. Then we consider this logic is more expressive than the typical timed automata, because let's say if one timed automata represent one exact time transition system, this logic is actually defines a set of exact time transition system, and typically this set is an infinite set. So this the motivation of defining a set of exact transition systems is sometimes we cannot estimate what's the what is the certain value of a certain time bound. Rather, we know an interval of it. So in that case, this logic is useful here. Okay. Before we talk about the target language hiphop.js, I want to introduce you. There are three typical computation models. The first one is the most classic one, is a sequential programming style. The second one is a synchronous concurrent programs. It is used on the context that sometimes you have some operation. For example, you want to query the server or you want to query the database, will take some time, but you don't know how long that it return. So it allows you to have this a non-blocking program. It only blocks the program until the return result is needed. And the last one is the synchronous reactive program. It reacts to the external events in a conceptually instantaneous and deterministic way. So for both of them, it's represented by JavaScript and Astera. Then hiphop.js is the combination of both. To better understand what's the difference made by combining these two languages, let's look at the first example. So if one thread generates a trace a 3-time instance with A and B and C, then the second thread, it generates W, X, Y, Z. Then the parallel of these two threads in a synchronous programming style, it should generate AW, BX, and CY and Z. So it actually zips all the time instance from different threads till the end, the last threads to finish. Then adding the asynchronous primitives is actually here. So at some point we need to wait for the event to be generated. So here when we are parallel these two threads, firstly we get AE. Then because then we are waiting for this signal C to be happen. Because the second time instance does not consist of C, so we'll keep waiting there till we get a C, and we synchronous at the third time instance and continue to synchronous the next time instances like D and F. And the last example shows that if, let's say, one thread generates ABD without having C, but the second thread is actually waiting for C. So the combination of these two threads is actually AE, then B. I'll keep waiting till the end of the first thread, and we will concat the rest of the part into the execution. So when we are having a hanging waiting signals there at the final effects, this is actually shows some programming problems here. So this is called broken chain promises in the JavaScript anti-pattern proposed in Uppsala paper 2017. All right. Then next part, we want to show you a running example of our techniques. So this is an example of hip hop modules. We have a main function here, and the calling function, we call it the cook. Then we specify the specifications in a style of like having requires and ensures corresponds to precondition and post condition. So in this, in the main function, firstly, the main function will generate two threads. The first one is waiting for the ready signal to be triggered, then emit go. In the second thread, we will emit the prepare signal first, and we have an asynchronous function call to call this function cook with the certain parameters. And after you run this program, we will trigger an event ready to indicate that this asynchronous program has finished. Then when we call this function cook, in this module, the precondition defines that D should be greater than 2000. And also the precondition contains a trace, means that before you enter into this program, the prepare signal has to be triggered in the current time instance. Then in the post condition, we ensure that we will have two time instance, which is bounded with the time value T, and T is smaller than the input value D. Right. So next, we will be going through the effects inference process of this function main. From the first branch, we use this triangle parentheses to represent the program states. So we initial the program states using the precondition of the program. So here, the first thread we start from true and empty trace. Then when we wait for a signal, adding the waiting signal into the trace. And if we're emitting some signal, we just add the events into the current time instance, like here. Next, from the second thread, it's the same way emit, we add into the time instance. And now we are calling a function with the parameters. So here, we want to check that if the current effects states satisfy the callee's precondition or not. So obviously here, the parameter we provide is 3000. It's greater than the precondition required from the callee function cook. Also, before enter before calling the function, we have triggered the events called prepare. So the precondition satisfies. So the term writing says that succeed. Then once the precondition satisfied, we will concat the post condition of the callee function into the program states directly. Then after some normalization operation, at the end of the verification, we want to check that if the final effects satisfy the program's post condition or not. So on the left-hand side, this part is the effects we generated from this inference. And the right-hand side part is the post condition we specified from the program. Then we want to check the inclusion inclusion relationships between these two time effects. Next, we will be using this example to demonstrate our term writing process. So given the formula here, we first do a renaming to distinguish the term from the left-hand side and right-hand side. So we rename it to TL and TR. Next, because here this TL bounds two time instance, so we want to do a split to assign a TL1 and TL2 to prepare signal and the cook signal. In the meantime, we want to add a side constraint such that TL1 plus TL2 equals to TL. Next, we want to do several times of unfolding. So here, when we are unfolding means that we want to eliminate the same time instance from the head of both hands. So here we want to eliminate, for example, we are eliminating this cook from the both sides. So when we are eliminating them, we will add the unification formula into the set constraints, says TL2 equals to TR. All right. So following those rules, which are automated in our tool, at the end, it is expecting to reach a base case. So here is the empty trace will be included in a cleaning star construction. So cleaning star means 0 or many times of repeat. So of course, empty trace will be included in this formula. Then in the meantime, we want to check that if the set constraint satisfies or not. So here we say TL smaller than 3, then TL1 and TL2 are the partial part of TL. Then TL2 equals to TR, so we can infer that TR is actually smaller than 3 in a way that we prove that this program is checked. All right, we prototype the system. We provide the open source code, and the implementation is based on OCaml, and the constraints is leveraged using the Z3 solver. And we check the correctness of our semantics model using two benchmarks. The first one is a CEC. It is a Astero language compiler. It's open source, and it provides some testing cases. The second one is we found this benchmark from this hiphop.js, this paper. They have some examples to test hiphop.js, this language. Then we prove the backend solver to be sound and complete as well. In summary, the most interesting contribution in this paper is we designed this novel logic, which is called time synchronous effects. In the sense that it goes beyond timed automata because it defines a set of exact time transition systems. The second one is we provide this automated forward verifier to provide a semantics model for hiphop.js, which is the first semantics model. And the last one is we provide this efficient term writing system to solve the inclusions between these timed synchronous effects, and we prove it sound and complete. All right, thank you so much for your attention. And at last, I want to thank all my peer PhD students for their time and efforts on organizing this research week. Thank you so much.
Hello, thank you, Yahui. And yeah, so thank you for the great talk. And if you have, you can start posting the questions in the chat box. So let's wait for a minute for some.
Thank you so much. I hope the presentation somewhat inspire some of the interests of programming verification.
Yeah, I mean, I actually, yeah, it was really explanatory. I mean, I learned a lot about from, yeah,
Thank you so much.
Yeah, I learned a lot from the presentation. Thank you. So,
I think while we are waiting, I guess there was one common question that was normally being asked, that because we are working on something on top of a new design language, so people may ask that what if this language is not very useful or not very popular, and then the verification might be a bit maybe not that useful either. Oh, we got a question.
Yeah, question. Yeah, so
can the technique of effect based on verification be extended to other languages? Are there any complications that might arise as a result of changing the language from JS? I think the direct extension is you can adapt to JavaScript directly. This is at least because we have this effects logic, which has the weighting signal, and we have many normalization rules. So sometimes we can detect this broken chain that when you have this asynchronous weighting, so that if, let's say, you are waiting for a signal which may never be triggered, it can be detected. Or you have triggered some signal which is supposed to be weighted, which is not used anywhere, which also can be detected. And there are some other anti-patterns.
Interesting. Thank you.
And another extension is it can also be extended to the synchronous languages. For example, like the Astera. So it can reason about the behaviors of synchronous language as well. And of course, the combination of them.
Right.
Changing the language from JavaScript, you can adapt it to any other asynchronous languages. For example, C#. There are many more and more languages introduce asynchronous primitives. Yeah, as far as I know.
Yeah, so I think this is also on similar lines to what you were telling earlier, that even though you're using a new language, it's still applicable to all of these other other languages and other paradigms.
Yes. Yeah, back to the question that what if you have a new language that maybe may not useful. I guess from the keynotes yesterday, Prof. He also mentioned that it is quite important and useful to design new programming abstractions and program models. So definitely it is worthy to explore more and see if we can benefit from combining different programming paradigms.
Right. Yeah. Yeah, makes sense. Right. Yeah. Thank you.